Alright, this video is from Chapter 4, Section 3, and the title is Trigonometric Functions of Any Angle. Some things you're going to learn about. We're going to learn about trigonometric functions of any angle, trigonometric functions of real numbers, we're going to look at periodic functions, and we're going to look at the 16-point unit circle. And while you will learn this, extending trigonometric functions beyond triangle ratios opens up a new world of applications. So, just to get some vocabulary out of the way here, when we talk about an angle, we have what's called the initial side, and then we have what's called the terminal side. The initial side is kind of like where the angle begins, I guess, and then as the angle opens up, however far it opens up in degrees or radians, that new ray is called the terminal side. So once the angle, and this letter here that you see, this is the Greek letter alpha, and we use alpha a lot of times as a variable of angle measure as well. So we have theta and alpha that we use. So if you recall, standard position of an angle, when we looked at angles in the first quadrant, the initial side would be on the x-axis, and the terminal side would be the ray that produces the angle of the given measure, whatever that happened to be. So we can talk about positive angle measure, and we can talk about negative angle measure. We have angles with the initial side on the x-axis, and here we have the angle alpha, angle opening up, terminal side here. This angle has a measure of alpha degrees, whatever that is, but the angle measure is positive. All right, and over here in B, we have the initial side, and then the angle is formed by rotating our angle clockwise, beta degrees, however many that is, but that would have a negative angle measure. So when we go counterclockwise to produce our angle, that's a positive angle measure. When we go clockwise, that produces negative angle measure. Okay, so some terms here, some extra terms. We can talk about coterminal angles. Two angles in an extended angle measure system can have the same initial side and the same terminal side, yet have different measures. Such angles are called coterminal angles. And this should make sense because we could have an initial side and a terminal side, whatever the angle measure is, and there's two different ways that we could rotate our terminal side to get to that angle. We could rotate it clockwise or counterclockwise, and that leads to this term coterminal angles. So one thing you may be asked to do are find a positive angle and a negative angle that are coterminal with 45 degrees. So how would we go about figuring that out? Well, let's take a look at this visually first. Here we have a 45-degree angle, right? So the question is, how can we get to 45 degrees? How can we produce an angle that looks just like this, but doesn't have a measure of 45 degrees? So that's the problem. That's what we have to figure out. So if we use this concept of coterminal angles, the 45-degree angle is generated by starting here at the initial side and going here. That would be our angle. But we can also go clockwise, starting here and rotating all the way around to this point. So what would that measure be? Well, we can figure that out. One complete rotation around would be 360 degrees. We're not going 45 degrees, so we should be able to calculate that. So there's one. What's the other one? How can we get the other one? So how can we get to this? Well, the other thing that we have to talk about and we looked at is we can rotate more than 360 degrees, or we can rotate more than 2 pi radians. So that's what this is going to involve. We could actually generate an infinite amount of angles that look like 45 degrees, an infinite amount of coterminal angles with 45 degrees in this way. So here's the illustration. The green rotation, okay, we get our negative 315 degrees. What we can do here is we can rotate all the way around 360 degrees, and then another 45 degrees, and that's the 405 degrees. So there's a visual of that. Now let's talk about how we would calculate this without a visual or a graph. Basically what we need to do is just add 360 degrees to 45 and subtract 360 degrees from 45. So those two angles are coterminal with 45 degrees. So find a positive angle and a negative angle that are coterminal with pi over 6. So anytime you see pi over 6, we're talking about angles in radian measure. So if we use that last example, what we did was we added 360 degrees and subtracted 360 degrees from our angle that we had. Now we're in radian mode. So think about what we need to do with this angle to find a positive and a negative angle that are coterminal with pi over 6. And if you said we need to add 2 pi and subtract 2 pi, you'd be correct. 2 pi radians is one complete rotation around a circle. It's the equivalent of 360 degrees. So if we add 2 pi to pi over 6, we get 13 pi over 6. If we subtract 2 pi from pi over 6, we get negative 11 pi over 6. So another example here, let theta be the acute angle in standard position whose terminal side contains the point 3,5. Find the 6 trigonometric functions of theta. Well, what I would do first is I'm going to ask you to pause the video and draw an illustration of the situation. And when you're ready, let's play the video. Alright, so here we have our point 3,5 right here. And we have an angle that's formed by the ray going through the point 3,5 and the x-axis, which the ray forming that angle on the x-axis we know is the initial side, and the ray going through the point 3,5 is the terminal side. So we want to write the 6 trig functions. Alright, so how do we do this though? We've got a point here and we don't know the angle. We don't have any information at all other than a point on the graph. Well, here's the trick. We've got the angle here and we have to make a right triangle. Alright, so we've got our initial side and our terminal side. Let's go ahead and drop a perpendicular down to the x-axis. As soon as I do that, that perpendicular that I went down from 3,5 down to the x-axis forms a right angle with the x-axis. Now I have a right triangle, and now I have some lengths that I can use to then calculate the measure of the angle or set up these different trig ratios. So this is something that we're going to do many, many times. So we have this point 3,5. We know that this green segment that I just drew has a length of 5, and we know that from the origin to where that segment intersects the x-axis has a length of 3. And so we can use the Pythagorean theorem to find the hypotenuse of this right triangle. And then we will have the 3 sides of our triangle, and then we can write the ratios, the different trig ratios. So that's the process. That's called a reference triangle. Okay, reference triangle, you're going to hear that a lot. Very simple, but very powerful. So after we do this, we use the Pythagorean theorem to find that the hypotenuse that we had there had a length of square root of 34. So we can write our ratios. Sine theta is 5 over radical 34, which is approximately 0.857. Cosine theta is 3 over radical 34, which is approximately 0.514. And since we're using decimal approximations here, we don't need to worry about rationalizing the denominator. So tangent is 5 over 3, and here you see our cosecant, our secant, and our cotangent functions, which are just the reciprocal of the sine, cosine, and tangent functions. Alright, so trigonometric functions of any angle. Now, any angle, we're not talking about just acute angles in the first quadrant here. We're talking about any angle. So let theta be any angle in standard position, and let P, some point P, with coordinates x, y, be any point on the terminal side of the angle except the origin. So P can't be the origin. Let R denote the distance from P to the origin, i.e. let R equal the square root of x squared plus y squared. That's just the distance formula. That's going to give us the length of the hypotenuse of our right triangle. Okay, so the first question you might say, well, why the letter R? And we will get to that in just a moment. But the one thing that you're going to notice here is that the sine of an angle, any angle theta, is y over r. So it's the y coordinate of our point over r. The cosine of theta is x over r. Tangent of theta is y over x. And our cosecant is the reciprocal of sine. Our secant is the reciprocal of cosine. And our cotangent is the reciprocal of tangent. And you can see here we put restrictions on x and y where appropriate. Let's take a look at this here. Here we have a point P that has coordinates 6, 4. We can go ahead and label our right triangle that's here with legs 4 and 6, and we have this r value here. We could use the Pythagorean theorem to determine its value. It's radical 52. But radical 52 can be simplified a little bit. That simplifies to 2 radical 13. So based on the previous slide, we could write the sine of theta, the cosine of theta, tangent theta, and so on, just using these coordinates. So what you'll notice, and this is going to be very important, when we have this point, this P, the sine involves the y coordinate of that point. And so here we're going to write the ratio 4 over 2 radical 13, which simplifies to 2 over radical 13. The cosine ratio would be x over r, and this will equal 6 over 2 radical 13, which will simplify to 3 over radical 13. And of course, exact answers, we would need to rationalize our denominators, but for right now we're just writing these ratios. Tangent theta, 4 over 6, y over x, opposite over adjacent. The last example again was another first quadrant angle. We want to take a look at evaluating trig functions of a non-quadrantal angle, theta, which means non-first quadrant. So here are the steps, and so I'm going to give you the steps, and then we'll take a look at an example. So step 1 is to draw the angle theta in standard position. Again, initial side on the x-axis, being careful to place the terminal side in the correct quadrant. Without declaring a scale on either axis, label a point P, other than the origin, on the terminal side of theta. And this is just an arbitrary point P. Number 3, draw a perpendicular segment from P to the x-axis, determining the reference triangle. If this triangle is one of the triangles whose ratios you know, label the sides accordingly. If it is not, then you will need to use your calculator. Number 4, use the sides of the triangle to determine the coordinates of P, making them positive or negative according to the signs of x and y in the particular quadrant. Use the coordinates of P and the definitions to determine the 6 trig functions. Alright, so let's take a look at this. Find sine of 210 degrees without a calculator. So the first question is how? How do we do that? So we need to think reference triangles. So then the question becomes, well, where do we draw the reference triangle? How do we draw the reference triangle? And the first thing we have to think is, okay, 210 degrees, if we're starting at 0, which is the positive x-axis, we rotate around to 180, that's the negative x-axis. So we're going to rotate beyond that, down into the third quadrant. So what that looks like is, so if we start here, this is going to be the initial side of our angle. For 210 degrees, like I said, we're going to rotate around. Here's rotated to 90, rotated to 180, and then we're going to rotate around a little bit more into the third quadrant. And what we're going to do is we're going to go ahead and draw the terminal side. So here's the terminal side. Okay, so we have this angle is 210 degrees. All right. Now we want to find, what were we asked to find? We're asked to find the sine of 210. And so what we have to do is, first thing we have to recognize is this is 30 degrees right here. Okay, 30 degrees past 180. So what we've got to do is think, okay, I have a right triangle here. And the nice thing about this one is it's actually a 30, 60, 90 triangle. And so what we know about a 30, 60, 90 triangle, here, this would be our P point here. I don't even need to know the coordinates of those, because what I'm going to do is I'm going to use my reference triangle to determine the coordinates of P. I'm going to make P have certain coordinates. And what I'm going to do is I'm going to make the short leg 1, I'm going to make the long leg radical 3, and I'm going to make the hypotenuse 2. Because, again, P is arbitrary. And so I can make these measurements anything I want to, but I need the relationship among them to hold. And I know that if the short leg is 1, then I know the long leg is radical 3 times longer than it, and I know the hypotenuse is 2 times longer than it. So the coordinates of P for my example is going to be negative radical 3, negative 1. Okay, because I'm in the third quadrant, x and y have to both be negative. And so to find the sine of 210, well, we know the sine is y over r. Now, what we have to do is we have to use these negative values in this ratio. And this is just an explanation of that without the visual. It's always nice to have a visual. Alright, so here's an example. We want to find sine theta and cotangent theta by using the given information to construct a reference triangle. So here we're actually given the ratios, and we want to determine sine theta and cotangent theta. So A, we're told that cosine theta equals negative 8 over 17, and cosecant is less than 0. So if you think about that, if cosecant is less than 0, what that means is cosecant is the reciprocal of sine, and sine we know is y over r. So cosecant is going to be r over y. And if that's going to be less than 0, r is always going to be positive, so that means y has to be negative. So we're talking about a negative y value here. Okay, negative y value. That's going to be important to us. We have to use these little nuggets of information to help us figure these things out. In B, we're told that tangent theta is negative 1/2, and we're told that cosine is positive. So if cosine is positive, then that means that the x is positive here, and that means that the y has to be negative. That means sine has to be negative. So let's see how we use this information to determine sine theta and cotangent theta. So for part A, cosine theta equals negative 8 over 17, and cosecant is negative. Since cosine is less than 0 and cosecant equals 1 over sine is less than 0, the terminal side is in quadrant 3. So again, cosine is negative, sine is negative, that means x is negative, that means y is negative, we're in the third quadrant. Draw a reference triangle with r equals 17 and x equals negative 8. So in terms of our right triangle here, now again, right triangles, when we're just talking about the right triangle has positive measurements. But when we use that reference triangle to do our trig calculations, these become quadrant values. So that's why they're negative, even though they're sides of right triangles. The reference triangle just helps us set up the problem. So we find y to be negative 15. So sine theta equals negative 15 over 17, and cotangent equals 8 over 15. Part B, tangent theta equals negative 1/2. Cosine theta is greater than 0. Since tangent is negative and cosine is positive, the terminal side is in quadrant 4. And how we know that is because cosine corresponds to the x value. Sine corresponds to the y coordinate. So if cosine is positive, that tells us x is positive. So we have to be somewhere either quadrant 1 or quadrant 4. But since tangent is negative and cosine is positive, that means sine must be negative. So we're talking about the fourth quadrant. so y is negative. So we draw a reference triangle with x equals 2, y equals negative 1/2. So here's our reference triangle. Use the Pythagorean theorem to find r. R is radical 5. So sine theta equals negative 1 over square root of 5, which is approximately negative 0.447. Cotangent of theta equals negative 2 over 1, which is negative 2. So again, we have to use the information that we're given. We have to determine what quadrant we're going to be in. We have to draw our reference triangle, label it accordingly, and then write the appropriate trig ratios. Alright, so here is our first big item of trig that's going to come in handy all throughout pre-calculus, all throughout calculus. It's called the unit circle. And the unit circle is a circle of radius 1 centered at the origin, and that seems pretty simple. But recall R. We said R was the hypotenuse of a right triangle for some random point P. So let me draw on here. If I drop a perpendicular to the x-axis, here's our right triangle, here's our reference triangle. So this is like our point P. And no matter where P is on the unit circle, if the radius is 1, that means R is 1. And that has some implications. If R is 1, remember, sine of theta, whatever this angle theta is y over R. Well, if R is 1, then that means sine theta is just y. Cosine theta is x over R. So think about what that means. If R is 1, then cosine theta is just x. So on the unit circle, cosine theta equals x, and sine theta equals y. So when we start talking about unit circle, radius 1, point P, no matter where it is on the unit circle, coordinates x, y, equivalent coordinates are cosine theta, sine theta. So that's a very big connection that we need to make as we move forward. So trig functions of real numbers. Let t be any real number, and let P, with coordinates x and y, be the point corresponding to t when the number line is wrapped onto the unit circle or around the unit circle as described above. So back to the unit circle, if you picture taking a number line and wrapping it around the unit circle to some value t, then, and this is what I mentioned, sine t equals y. Cosine t equals x. So some t value, no matter what t is, meaning no matter what the angle is, sine is going to equal y, cosine is going to equal x, tangent is going to equal y over x. And here we have our reciprocals of those. So t can be a value, an angle value, in degrees or radians. And so what that t value is, that t value tells us where our radius of our unit circle is going to be drawn to, forming the angle theta that we can then use to write the different ratios. And based on this t value, we can develop these functions called periodic functions. And so we're just going to define a periodic function right now, and we're going to take a look at these much more in depth in the next lesson. But a periodic function y equals f of t is periodic if there is a positive number c such that f of t plus c equals f of t. Meaning if you add something to the input, okay, or the domain value, you add a value to it, and it equals that same value before you added the other value, then we have what's called a periodic function. So for all values t in the domain of f, that's true if it's periodic. The smallest such number c is called the period of the function. Okay, so here we have it's called the 16-point unit circle. And this is something that you're going to want to probably have copied down in your notes, and I will post some images of this on Schoology as well. But this is something that we're going to use time and again, and it's something that you're going to want to try to commit to memory as much as possible. If I were to draw a radius from the origin out to this point here, what I've just created is I've just created a 45-degree angle, and the equivalent of a 45-degree angle is a pi over 4 angle in radians. Okay, so 45 degrees is the equivalent to pi over 4 radians. And what I can do is I can talk about the sine and the cosine of that angle. And there's my reference triangle. And what I could do is I could say, all right, I've got a right triangle here. This angle is 45. I could use what I know about right triangles, and the two legs are congruent to each other. And I could figure out, what the legs are, and I could write sine, cosine, tangent, whatever. But on a unit circle, 45 degrees, cosine is radical 2 over 2, sine is radical 2 over 2.